Hey, what's up everyone? Alex here with GMAT Ninja. Welcome to our Quant video, Number Properties Part 1. So the goal of this video is to talk about the basics of number properties, things like greatest common factor, least common multiple, divisibility, remainders, even odd logic. Now this video is going to consist of 6 questions. The first 3 are probably going to feel like warm-ups to these topics, and then questions 4, 5, and 6 are going to be a bit more challenging, introduce some wrinkles. And the way I think of it is, if you're shooting to break an 80 on the quant section, these are all topics you want to be familiar with. Now, number properties shows up pretty regularly on the quant section, a lot less so on data sufficiency, data insights. So this video is going to consist exclusively of multiple choice problem solving questions like you'd see on the quant section. So the way it works is I'm going to put a video up there for about 2 minutes, give you a chance to solve it, and then I'm going to go through a solution afterwards. All right, great. Let's take a look at the first question.
Hey everybody, Charles here. Sorry for the interruption. Before we get you back to that quant content, 3 quick things I'd love for you to be aware of. First of all, this video is part of our full, free, complete GMAT course that's available up on our YouTube channel. If this course is saving you money that you would otherwise spend on a course or a tutor, please consider donating some of that savings to charity, either a charity that you love. If you don't have a charity that you love, we've got a list of charities that we love to support on our website, gmatninja.com. Second thing, if you love that presenter that you're watching in this video, not me, the other one, they offer one-on-one tutoring. If you're interested in that, gmatninja.com and we can set you up. Third thing, finally, if you're doing great on the GMAT, doing great on the GRE, starting to look for admissions help with your applications for grad school, we would love to refer you to a bunch of our favorite companies. So just hit us up. There is a contact form on our website, gmatninja.com. Also, a link in the video description. Just fill that out. We'll send you a list of our favorite admissions consultants, not just at our company, no strings attached, not going to sell your email, not going to try to sell you anything. We just want to make sure if you've put in the hard work on the GMAT, that you end up in the best possible hands if you need help with your applications. All right, that's it. Enjoy the quant.
All right, so before we dive into this one, I just want to think about a number properties idea in general, which is, well, how do I want to be approaching these questions? Do I want to use the quote-unquote smart method, where I'm using algebra and formulas and that sort of thing? Or is it better to use the quote-unquote stupid method, where I'm just writing things out, looking for patterns? And the answer is, well, it really depends. Sometimes it's better to be formal and use algebra. Other times that's not going to work and you want to write things out and look for patterns. So bottom line, you don't want to get addicted to one method over the other and just use it every single time no matter what. Much better to stay flexible. Take a step back and always ask yourself, well, what tool is going to work best for this particular question? Okay, so with that in mind, let's take a look at this one. You and your partner set your alarms for 6 a.m. If your alarm repeats every 12 minutes and your partner's alarm repeats every 18 minutes, at which of the following times could both of your alarms go off? Now, I could certainly imagine using the quote-unquote stupid method for this one. I just write out the times that my alarm goes off, 6, 6:12, 6:24. Same thing for my partner's alarm clock, 6, 6:18, and so forth. And then I just compare the lists and see, well, what are times that both the alarms would go off? And I notice that the numbers don't go all that high here, so presumably I shouldn't have to write out all that much stuff to reach an answer. So here, yeah, an informal method works great, but just to learn some number properties concepts, I'm going to go through a more formal approach. Even if it's not strictly necessary on this one, it's going to give us some useful tools, especially as the questions get harder, the numbers get bigger, that kind of thing. Okay, so if I think about it, what I'm essentially looking for here is a number that's a multiple of both 12 and 18. Okay, a number that's a multiple of 12 and 18 is going to be a time that both the alarm clocks would go off. So that gets me thinking about least common multiple. So let's explore that a bit. What would it mean for something to be the least common multiple of 12 and 18? So let me imagine a number x that's a multiple of 12. And how could I represent that with an expression? Well, if x is a multiple of 12, I guess that means that 12 is a factor of x. So I could write it as x divided by 12 has to give an integer if 12 is a factor of x. And I could say the same thing for 18. If x is a multiple of 18, then 18 is a factor of x, and x over 18 is going to have to give an integer. Okay, so the question now is, what's the least value of x that would satisfy both of those statements? So to help figure that out, let's do prime factorizations of 12 and 18. Okay, so I'm going to break down 12 and 18 into their prime factors. So 12 would be 4 times 3, 4 is 2 times 2, so 2 squared times 3 is 12. 18 is 9 times 2, which is 3 squared times 2. Okay, 3 squared times 2, that's 18. Now, one thing I like to remind myself is that 18, 3 squared times 2, those are just two different ways of notating the exact same number. The difference is this way of notating it gives me a whole lot more information. So that's why I'm going to write 12 and 18 in terms of their prime factorizations. Okay, so I'll replace 12 with 2 squared times 3, and I'll replace 18 with 3 squared times 2. Okay, so now my question is, what's the value of x that would be divisible by both this number and this number? So let me start with this one and think about the 2's. How many 2's is x going to need to be divisible by 2 squared times 3? Well, it's going to need to have 2 2's. Okay, what about 3's? Well, it's going to need to have at least one 3 over here, but if I go over here, I notice, well, this has 2 3's. Okay, so to be divisible by 3 squared times 2, it's going to need to have a 3 squared. And notice, now I'm totally covered for both these numbers. 2 squared times 3 squared would be divisible by this. 2 squared times 3 would also be divisible by this. Okay, great. So there's my least common multiple of 12 and 18, 2 squared times 3 squared, otherwise known as 36. Okay, so here's a sort of shortcut way of thinking about what I just did to find the least common multiple. I took the prime factorizations, and then I went to each of the factors, and I picked the larger exponent version of each factor. So 2 is a factor, the larger exponent version between 2 squared and 2 is 2 squared. Between 3 and 3 squared, the larger exponent version is 3 squared, and again, that leads me to my least common multiple of 12 and 18. Okay, so let's do that same process for a slightly bigger number. Just going to introduce a slight wrinkle that sometimes can throw people off. So 60 and 18, what's the least common multiple of those two numbers? Well, if I prime factorize 60, that's 2 squared times 3 times 5. That would multiply to 60. So let me replace my prime factorization here with another 5. Okay, so now I've got this set up to find the least common multiple of 18 and 60. So if I go through my process, well, I'll pick the lower exponent version of each factor. So for 2 squared and 2, it's still 2 squared. For 3 squared and 3, it's still 3 squared. But what about for 5's? Well, this one has a 5, this one doesn't. So I guess the larger exponent version of 5 and no 5 would be just a 5. Okay, so if I multiply all those out, I get 36 times 5, that gives me 180. So there's my least common multiple of 18 and 60. Okay, now for these small numbers, this is stuff that sure I could probably find by trial and error, just writing things out. But as the numbers get bigger, if I want to find, say, the least common multiple of 3 big numbers, this tool can come in handy. Okay, so before we go back to the question, let's explore the idea of greatest common factor, which is quite related to the idea of least common multiple. Okay, and what's the idea there? Well, the greatest common factor of 60 and 18 would be the biggest number x, let's call it, that goes into both 60 and 18. So I'll write it kind of in a similar but opposite way. You could say to least common multiple. If x is a factor of 60, then 60 over x is going to have to give an integer. If it's a factor of 18, then 18 over x has to give an integer. And what's the greatest value of x that would make both these statements true? Okay, so let me again replace these numbers with their prime factorizations. So I've got 2 squared times 3 times 5, and 3 squared times 2. Okay, so at this point, I'm going to go through sort of an opposite process to what I did for least common multiple. I'm going to go through each of the factors here, and I'm going to pick the smaller exponent version, right? For least common multiple, I pick the greater exponent version of each factor. Here it's the smaller exponent version. So for 2's, I've got and this should be a 2 squared. Between 2 squared and 2, the smaller version is 2. Okay, so x can have at most 1 2 in it, right? If it had 2 2's, it wouldn't go into this number here. What about between 3 and 3 squared? The smaller exponent version is 3. If I had a 3 squared, it wouldn't go in here, so I can't have a 3 squared. What's the smaller exponent version of 5 and no 5? I'm going to pick no 5, right? If I had a 5 in x, it wouldn't go in here. This wouldn't be a true statement. So there's my greatest common factor of 60 and 18. It's 2 times 3, otherwise known as 6. Okay, great. So least common multiple, greatest common factor. Those are the methods for finding those. Now let's go back to this question. Okay, so I went off on that tangent thinking about what's the least common multiple of 12 and 18, because those are times that both these alarm clocks will go off, and we said the least common multiple of those two numbers was 36. Okay, so these alarm clocks are going to go off at the same time every 36 minutes. So they're both going off at 6 a.m., and every 36 minutes after that they're both going to go off. So they would both go off at 6:36 a.m. Okay, now I notice that's not up here. So I might have a moment of panic if I misread the question, right? If I was thinking, well, what's the first time they're both going to go off? That would be 6:36, but notice that's not what they're asking. They're just saying, which of the following times is one where they could both go off, okay? So they could both go off at 6:36, but there could be other times too. Every 36 minutes, they're both going to go off. So what's 36 minutes after 6:36? That would be another time they'd both go off, 7:12. That's not there, no big deal. I'll just add 36 again, 7:48. Oh, and there it is. D is 7:48. So the correct answer on this one is D. Okay, so what do you want to take from this question? Well, those fundamental number properties concepts, greatest common factor, least common multiple, prime factorizations, breaking numbers down into their prime factors, knowing the difference between a factor and a multiple, all that stuff, really key, shows up all the time on number properties questions, so you want to be really comfortable with that. The other general thought, well, again, this idea, smart method with formal algebra, that kind of stuff, or stupid method, writing things out, looking for patterns. Be aware of both of them. Don't get addicted to one over the other. Stay flexible and ask yourself which one is going to be most appropriate for a particular question. All right, so using all that logic, again, that leads us to the correct answer on this one of D. All right, great. Let's take a look at the next question. All right, let's take a look at this question. X is a multiple of 63 and is divisible by 24. Which of the following is a possible value of X? And I've got some numbers to choose from. So maybe I'll start this one by trying to get some kind of translation of this language up here. Can I turn that into a math expression, something that I can work with? So X is a multiple of 63. Okay, so 63 times something is equal to X. So I guess that also means that 63 has to be a factor of X. Okay, so I can translate that this way. X over 63 has to be an integer. Okay, now let me go to the next portion. X is a multiple of 63 and is divisible by 24. Okay, so if X is divisible by 24, I guess that means 24 is a factor of X. 24 is a factor of X. X is a multiple of 24. So I'm really kind of just saying the same thing again about 24 as I said about 63, but just using different words. So that's sort of a theme in these number properties questions. I'll get the same concepts again and again, but wrapped in different language. So I want to be comfortable going back and forth between multiple and factor and divisible and all that stuff. So anyway, I've got a translation of the initial portion of the question. I know that X has to be an integer if divided by 63 and 24. It's a multiple of 63 and 24. So, okay, smart method or stupid method? Do I want to just start writing stuff out, see if I can get to an answer, do something more formal? Well, I notice these numbers are pretty big. That's a strike against the stupid method. And, you know, multiples of 63, that's going to get ugly pretty fast. Okay, so that's going to be a headache. I don't want to start writing out all the multiples of these numbers, trying to get one of these answer choices. I'm going to do something a bit more formal. So, okay, a multiple of 63 and 24. Well, I suppose a good place to start would be to find the LCM, least common multiple of 63 and 24. And, you know, maybe that's going to be the answer. But even if it's not, if I know the least common multiple of two numbers, then I can use that to find all the other multiples of those two numbers. So let's start with that. 63 and 24, I want to break these down into their prime factors. And then I can use their prime factors to get the least common multiple. Okay, so 63 is 3 squared times 7. And let's see, I get 2 cubed times 3 for 24. Okay, so like we did last time, we're going to go through each of the factors and pick the larger exponent version. So between 3 squared and 3, I want to pick 3 squared. Between, say, 2 cubed and no 2, I want to pick 2 cubed. And between 7 and no 7, I want to pick 7. So there's my least common multiple. And I suppose, you know, maybe that is one of these numbers up here. I'll just multiply this out to find out. So let's see, this is 9 times 8 times 7. 9 times 8 is 72 times 7. Okay, 70 times 7 is 490. 2 times 7 is 14. So I get 504 is the least common multiple of 63 and 24. So I noticed that's not up there, but again, that doesn't mean I did something wrong necessarily. They're not asking for the least common multiple. We're just trying to find something that's a multiple of 63 and 24. So this could help me find all the other multiples as well. You know, 504, plausible answer, just doesn't happen to be there. So can I find what are some other multiples of 63 and 24? And here's how I'd go about doing that. So this is equal to 504 here. This is the least common multiple. Now, any multiple of this number would also be a multiple of 63 and 24. And why am I saying that? Well, I know 63 would go into this. I know 24 would go into this. And if I multiply it by something else, I include, you know, some other number here, 63 and 24 are still going to go into it. So it's totally legal to add other multiples. In other words, any multiple of 504 also going to be a multiple of 63 and 24. Okay, so what are some multiples of 504? Well, the next one up is 1008, and I can't help but notice that's answer choice C. I can quickly notice, well, none of these other answers are multiples of 504. That just confirms I was doing everything right. So, okay, we can be confident the correct answer on this one is C. Okay, so what do you want to take away from this one? Well, this is a good example of the smart method really trumps the stupid method. Writing all these multiples of 63 and 24, that's going to get ugly pretty quickly. Finding the LCM, nice and neat. I get to the answer pretty fast. And again, just that idea of translating this word soup, you could say, into some nice, neat algebra type expressions. And that can kind of get me started. Again, leads me to the correct answer on this one of C. All right, great. Let's take a look at the next question. All right, let's take a look at this one. What is the remainder when 3 to the 37 is divided by 10? Okay, so we've got this concept of remainder. So here's a quick review of that for anyone who wants a review of remainders. So let's do a concrete example. How about if I do 27 divided by 8? Okay, so what's the remainder there? So what I'm asking myself is, well, I try to get 8 as close to 27 as I can, and then however much I fall short, that's the remainder. So how close can 8 get to 27? Well, 8 times 3 is 24. That's pretty close. If I multiply 8 times 4, I get 32. That overshoots. So that's no good. So 24 is as close as I can get to 27 using 8, and I fall short by 3. So I could say 27 divided by 8 is equal to 3 with a remainder of 3. Okay, 8 times 3 is 24. 24 is 3 short of 27. Okay, let's just do one or two more examples to kind of solidify that logic. 27 divided by 5. So the closest that 5 can get to 27 is 25. Okay, and then 25 is 2 short. So I would say, okay, in this case, I've got a remainder of 2. So 5 into 27 is equal to 5 with a remainder of 2. Okay. One more just to wrap things up. What about 27 divided by 9? Well, notice 9 actually goes into 27, so I could say, well, okay, the closest I can get to 27 is 27, so 27 divided by 9 is equal to 3 with a remainder of 0. So now notice, in a way, we're introducing this new idea of, well, with a remainder of 0, really what I'm talking about is factors, okay? So we'll just add that to the list. You know, I could say 9 is a factor of 27, 27 is divisible by 9, 27 is a multiple of 9, or when I divide 27 by 9, I get a remainder of 0. Those are all telling me the exact same relationship. Okay, so we've nailed down the idea of remainder. So this question is asking, I'm going to divide 3 to the 37 by 10. So how close can 10 get to 3 to the 37? And then how much am I going to fall short? So I'll write that out. But I'm immediately noticing, well, this is such a huge number. I can't just kind of figure it out the way I was with those smaller ones. So now the question is, what am I going to do about that? I've got this big crazy number, 3 to the 37. What's the remainder going to be when it's divided by 10? So let me pick some examples of numbers to divide by 10 and see what the remainder is and see what I can learn from it. So maybe I'll pick 13 divided by 10, and bigger number, I don't know, how about 541, divide that by 10. Okay, what's the remainder in each of these cases? Well, 10, how close can that get to 13? Well, it can get to 10. I'm going to fall short by 3, so I've got a remainder of 3 in that case. Here, well, how close can 10 get to 541? Well, it can go into 500, it can go into 540, so I've got a remainder of 1. So I'm noticing it looks like if I divide a number by 10, the remainder is going to be equal to the units digit. And why does that make sense? Well, if you think about it, you know, 10 goes into 100, so no matter what the hundredths digit is, it's going to be able to go into that. 10 goes into 10 or any multiple of 10, so it's going to go into the tens digit. So whatever we're left with here in the units digit, that's how much we're going to fall short by. Okay, so that takes me a little bit farther. What I'm looking for here is, what is the units digit of 3 to the 37? That'll tell me, well, when I divide 3 to the 37 by 10, what's the remainder? Okay, so I've simplified the question. What's the units digit of 3 to the 37? Well, again, I run into this problem of, well, that's a huge number. I don't know off the top of my head what 3 to the 37 is. Okay, so then let's do some concrete examples, sort of start writing things out, see if we can find a pattern that'll help us figure out what is this units digit. Okay, so I'll write out some powers of 3, and maybe from what I write down, I can kind of extrapolate what would the units digit be of 3 to the 37. Okay, so I'll just translate these here. Okay, 81 times 3, 243 times 3, let's see, that's 600 plus 120 plus 9, so 729. 729. Okay, so I could keep going, but let me just stop and see, do I have a pattern yet? Okay. So I'm interested in the units digit of 3 to the 37. What do I learn about the units digits of powers of 3? Well, 3, 9, 7, 1. Aha, back to 3, and then a 9. Okay, I'm betting I'm going to have a 7 and a 1 here. So let's see if that's the case. Well, 729 times 3. Okay, well, 9 times 3 is 27. Okay, and then everything I do after that is just going to determine the other digits, the tens digit, the hundreds digit. So really, if I multiply the units digits, that's going to give me the units digit of the product. Okay, cool. So 9 times 3, 27. So the units digit of this number, whatever this big number is going to be 7. Same logic here. 7 times 3, 21. The units digit of 3 to the 8th is going to be 1. And that confirms the pattern I suspected, which is every 4 numbers, the pattern repeats. Okay, so now I've got a pattern of 4 here. So let's see if I can leverage that number 4. I know that 3 to the 4th is 81. 3 to the 8th is some number ending in 1. Okay, so it looks like 3 to some power that's a multiple of 4 will have a units digit of 1. So I suppose 3 to the 12th would also be 1, and 3 to the 16th would also, have a units digit of 1. Okay, so where is 3 to the 37 going to fall in that pattern? You know, I don't really want to write out every single one. I might make a silly mistake. So can I use logic to figure it out? Well, okay. If the power is a multiple of 4, it's going to have a units digit of 1. It's going to be at that point in the pattern. So what's a multiple of 4 that's really close to 37? Well, I guess that would be 36. Okay, so 3 to the 36 is going to have a units digit of 1. So that puts me here in the pattern. So what about 3 to the 37? That's 1 farther. Whatever that big number is, it's going to have a units digit of 3. Okay, so 3 to the 37 has a units digit of 3. If I divide it by 10, by the logic I was discussing earlier, I know the remainder is going to have to be 3, equal to the units digit. So there we go. The answer for this one is B. Okay, so what do you want to take from this question? Well, good to be comfortable with the notion of remainders, but on top of that, smart method or stupid method, what did I use here? Well, I think it's kind of a combination of both, right? It's good to know, I think, this concept, well, if I divide something by 10, the remainder is just going to be the units digit. Maybe that's not a good thing to have at my fingertips. But I certainly didn't know just off the top of my head. Well, here's how, what the units digit of 3 to the 37 is. There's some experimentation, right? I write out a pattern, I write out some numbers and find the pattern and extrapolate to the conclusion here. Okay, and just one more point about that. As you might imagine, this doesn't just work for 3. No matter what number I pick, if I go through all the powers of it, it's going to start repeating at a certain point. And you can do some examples to prove that to yourself, but I'll just write out powers of 2 here. So 2, 4, 8, 16, 32, aha. So just like with 3s, after 4, I'm back to the pattern. The units digit is going to be 2. 2 to the 6 is going to have a units digit of 4, and then 8, and then 6, and so on. Okay, great. So using all that logic, we get to the correct answer on this one of B. All right, great. Let's take a look at the next question. All right, let's take a look at this one. If p, q, and r are positive integers such that p is a factor of q and p is a multiple of r, which of the following must be an integer? And I'm given some expressions with p, q, and r. Okay, so let's see if I can translate some of this verbiage into some useful algebra math stuff to try to evaluate this question. So p, q, and r are positive integers, good to know. P is a factor of q. Okay, so I guess that means q is divisible by p, so I could write that relationship this way. Q over p has to be an integer. Maybe I'll call that integer n, remind myself, okay, n is an integer. And this is one way to write this relationship. I could also write it like this: q is equal to n times p. I don't know which is going to be more useful, but maybe good to be flexible. I have either one if I need it. Okay, p is a multiple of r. All right, so I could translate that as r is a factor of p, or p is divisible by r, all that kind of familiar language. So I'll represent that as saying p over r has to be equal to an integer, but not necessarily the same integer, so I'll call it m instead of n, and I'll just remind myself n is an integer. And just like I did with q and p, I could rearrange this to say p is equal to m times r. Who knows which of these is going to be the most useful, but I've got them all if I need them. Okay, so now answer choice A, does this have to be an integer? So, well, what would it mean for p plus q over q to be equal to an integer? Well, kind of like we're saying, if p plus q is a multiple of q, or put another way, if q is a factor of p plus q, then this thing would be an integer. Okay, and then one more thing I want to draw our attention to: which of the following must be an integer? Okay, so I want that to jump off the page. They didn't say which could be an integer under certain circumstances, but which absolutely must be an integer no matter what. So that's what I'm trying to figure out. Does this absolutely have to be an integer? Okay, so just looking at it, I'm not sure, but I suppose if I do some substitution, I could get it in terms of m and n, which I know are integers, and maybe that'll kind of illuminate this quandary here. So okay, I could start substituting, but now I can't help but notice all my information here is written such like, q over p, p over r, things like that. I don't have any sums. So if there's any way I can make this look more like my information, maybe it'll be easier to start substituting and plugging in. So can I simplify this at all to make it look more like my information? Yeah, I can split up this sum, right? I have a sum over a single term. I can split it up like this. This is equal to p over q plus q over q. Okay, I'm starting to like this already because q over q is just equal to 1. So now I'm just asking myself, well, what about p over q? What can I say about that? And then is that going to yield an integer ultimately? So, well, I have something really similar to that, right? Q over p is equal to some integer n. So what would p over q be equal to? Well, I guess I'll just flip that. Q over p is equal to n, so p over q would be 1 over n. So what do I know about 1 over n? Does it have to be an integer? Well, I suppose it could be, right? If n is an integer, n could equal 1. 1 over 1 is an integer, but it doesn't absolutely have to be. I could think of a lot of values of n, integer values of n, that would make 1 over n not an integer. 1 over 2, 1 over 3, etc. Okay, so p over q, not necessarily an integer. So something that's not an integer plus 1 would be a non-integer. Okay, so p plus q over q, answer choice A, not necessarily an integer. So I can eliminate that. Okay, so let's move on to B. And I'm noticing, okay, looks like a similar pattern. I have a sum over a single term in the bottom. Maybe I'll split that up, and that'll make the algebra easier to work through. So I'll call this q over r plus p over r. And that's how I would translate answer choice B. Okay, so q over r, do I have anything directly about that? Don't see that. What about p over r? Yes, p over r is equal to m. That's good news. Okay, what about q over r? Well, okay, I can't deal with this directly, but maybe I can do some substitution. Okay, because q is equal to n times p. All right, maybe I'll try that. Q is n times p over r. It's another way of writing this expression. Now, I also know, p over r is equal to an integer m. So I could write, well, p over r is equal to m, so q over r is equal to n times m. So I have n times m plus m. And I know that n and m are integers. So an integer times an integer plus an integer has to yield an integer no matter what. That's got to be true. So the correct answer here is B. Okay. So, if I was taking a test, I might say, I'm really confident in that algebra. This absolutely has to be an integer. So I can move on to the next question. I don't have to agonize over C, D, and E necessarily. But, for the sake of practice, we might as well go through those now. Maybe we'll learn something as we go through those answer choices, some algebra lessons that might be useful to know, even if not totally necessary, I think, if I was actually doing a test. Okay, so C, okay, we got this pattern again, a sum over a single term. I'm going to split this up. I think that'll probably make this easier to analyze. And do I know either of these directly? Well, P over R is equal to M, so R over P is equal to 1 over M, okay. Might as well analyze Q over P. Yes, that's equal to N, so N plus 1 over M. Doesn't have to be an integer. Again, if M were equal to 1, sure, but M doesn't have to be equal to 1. I could think of lots of integer values of M that would make this expression not an integer. So C, nope, doesn't have to be an integer. I can eliminate that. Okay, what about D? Aha, D's breaking the pattern. So I don't want to get lulled into complacency here, right? I'm splitting all these up, but they're changing the pattern here. Can I split this up? If that very wrong-headed idea occurred to me, let me just nip that in the bud. I don't want to go down that path. And here's what I mean. If I was tempted to say P over Q, R over Q, is this expression equivalent to this? No, absolutely not, right? This would give PR over Q squared. I'm interested in PR over Q. Okay, so just a little sort of algebra review there, a little potential algebra pitfall. So now, what would it mean for PR over Q to be an integer? Well, if I think about it, if Q goes into P, it would be an integer. If Q goes into R, it would be an integer. Doesn't need to go into both, though. And let me just demonstrate that concept with some specific numbers here. 3 times 7 over 3. Well, that's equal to an integer. That's equal to 7. But 3 doesn't necessarily need to go into each of them. As long as it goes into one of them, it's going to be an integer. Okay, so what I'm asking myself is, I'll take them separately. Does P over Q have to be an integer? Well, I know that Q over P is equal to N, P over Q is equal to 1 over N. So no, that doesn't necessarily have to be an integer, but again, that's not disqualifying because maybe Q goes into R. So let's analyze that. Q into R, is that going to yield an integer? Well, I don't think I'm told anything directly about the relationship between R and Q, but maybe I could do some algebra substitution. So Q is equal to N times P, okay, R over NP, and I know that, right, P over R is equal to M, so R over P is equal to 1 over M, so this is 1 over NM, and that's not necessarily an integer. Okay, so Q does not have to go into P, Q does not have to go into R, neither of those has to give an integer, so this does not have to give an integer, so D can be eliminated. Okay, what about E? Well, sort of flips the pattern from previous ones. Instead of having a sum in the top, I've got a sum in the bottom. So does R plus P go into Q? Okay, so I can't split this up. Really, all I can do is substitute. So let's start substituting. Q is equal to N times P, okay, over R plus P. Okay, I notice a P in the top and the bottom, but I've also got this R. Well, maybe if I could substitute in for P, that would help get things all in terms of one variable, and I have P in terms of R. Okay, great, that'll do the trick. P is equal to M times R. So I'll call that M times R. Do the same thing in the bottom. P is M times R. Okay, great. I got everything in terms of R. That was my goal, so I can simplify it now. I can cancel all those R's, and I'm left with NM over 1 plus M. Okay, so does that absolutely have to be an integer? Just looking at it, I'm guessing no, but I can pretty quickly prove that. If I said, I don't know, 3 times 2 over 1 plus 3, that gives 6 over 4. So there's probably some ways that this could be an integer, but it doesn't have to be if n is 3 and m is, what was I picking there? I think m is 3 and n is 2. Anyway, I can pretty quickly find an example where it's not an integer. So e does not absolutely have to be an integer. So I confirmed C, D, and E. I can comfortably eliminate those. And again, that leaves me with the correct answer choice of B for this one. Okay, so what do you want to take away from all that? Well, just the idea of translation. Really big on the GMAT in general, really useful in number properties questions. I'm given this word soup about factors and multiples and things like that. If I can simplify it into some algebraic expressions, okay, it becomes a lot more straightforward. I can use substitution, churn through these, and again, end up with the correct answer choice of B. All right, great. Let's take a look at the next question. All right, let's take a look at this one. What is the smallest integer x such that 6 to the x is a multiple of 144? And I've got some options of x to pick from. Okay, so let's see if I can translate this into some expressions. 6 to the x is a multiple of 144. Okay, that means 144 is a factor of 6 to the x, or I could say 6 to the x is divisible by 144. So we know that sort of familiar language can be translated like this. 6 to the x over 144 has to be equal to an integer. Okay, so now at this point, well, what should I do? Sort of like smart method, stupid method? Do I want to start, trial and error, figure out what's the value of x that's going to make the statement true, smallest value of x that would make that true? Well, that seems like a lot of arithmetic, raising 6 to higher and higher powers. These get to be high enough that doesn't seem particularly pleasant, and then dividing by 144 seems kind of ugly. So let's see if I can deal with this in a more analytical way. Now, we also said if you break down numbers into their prime factors, gives us a lot more information about them. That might provide a path forward here. So let's try that. If I write everything in terms of prime factors, maybe that'll make this easier to break down. So 144 is 12 squared. 12 itself is 2 squared times 3. So 144 is 2 to the 4th. I've got 4 2's times 3 squared. Okay, and then 6 I could break down into 3 times 2 to the x. So, okay, here's a translation of this statement. This has to be an integer. Now, this looks pretty good. I've got everything in terms of 3's and 2's, but maybe I'll call upon an exponent rule to simplify the top even further. 3 times 2 all to the x power. I could call that 3 to the x times 2 to the x. So if that seems a bit surprising, you may want to check out our exponents video where we go into that kind of thing in more detail. But here, suffice it to say, I have two things multiplied raised to a power. That's each of them individually raised to that power. That works. Okay, so now I'm asking myself, what's the smallest value of x so that this thing on top is divisible by this thing on the bottom? So I'll start maybe with the 3's, 3 to the x. So what's the smallest value of x that would allow 3 to the x to be divisible by 3 squared? Well, obviously x is going to have to be at least 2 for that to be true. Now, could it be bigger than 2? Sure, that would still work. 3 to the third divided by 3 squared, that's, still going to give an integer, but at the very least, x has to be 2. Okay, now what about with the 2's? Well, there, at the very least, x is going to have to be 4, kind of by the same logic. So I have to pick just one value of x, the smallest value of x, that'll make both of those statements true if I want this overall to be an integer. Okay, so notice if I pick x equals 2, that's going to mess up the 2's. Put another way, 2 squared over 2 to the 4th, that's not going to be an integer. So x equals 2, that value of x is too small. Even though it would accommodate the 3's, it would mess up the 2's. Okay, so I'm going to have to go with x equals 4. 2 to the 4th over 2 to the 4th, that works. 3 to the 4th over 3 squared, that works too. Again, that's a bigger x than I need for just the 3's on their own, but that doesn't mess things up. And at the very least, x has to be 4 to accommodate the 2's. So, okay, long story short, yes, x equals 4, so answer choice C. 4 is the smallest possible value of x for 6 to the x over 144 to be equal to an integer. Okay, great. So what do I take from that question? Well, translation, multiple, factor, can I get that into some kind of algebraic expression that helps sort of pave the path forward? And smart method, stupid method. Again, that question, how do I want to proceed? Do I want to just sort of like write things out, look for a pattern? Not so much here, the numbers are a bit too big, that seems ugly and painful. Can I break things down to their prime factorizations and start using my logic at that point? And again, all of that leads us to the correct answer of C on this one. All right, great. Let's take a look at the next question.
All right, two last things. Thank you so much for making it to the end of the video. If you've made it this far, you're one of those awesome people that's obviously really engaged in this GMAT thing. We would love your comments and your feedback. If there's anything else you'd love to see in our videos, hit us up in the comments. We'll do our best to oblige. Second thing, if you're enjoying it, hit that like button, hit the subscribe button. Helps other test takers like you find our full free video course. You need anything else? You know where to find us, gmatninja.com. Thanks so much. Enjoy this last question.
All right, let's take a look at this one. If m and n are positive integers, and m plus n and m over n are both even numbers, which of the following cannot be an even integer? And I'm given a bunch of expressions with m and n. So let's see if I can translate this stuff, figure something out about m and n that will help me answer the question. So, okay, I'll take the first bit of information. M plus n is an even integer. Okay, so m plus n is even. what does that tell me about m and n individually? Well, this question is asking about even versus odd, so let me think along those lines. I suppose an even plus an even would give an even. An odd plus an odd would also give an even. But an even plus an odd or an odd plus an even would give an odd. So that scenario is out. So that tells me m and n have to either be both even or both odd. And you could do some examples if you wanted to prove those rules to yourself, but those are pretty solid rules about even and odd. So, okay, that gave me some information. Let's see if I keep going. Can I figure out anything more specific about m and n? Well, m over n, that's also even. Okay, so which of these two scenarios is consistent with this scenario? Could I have both of them be odd and give an even number? Could I have both of them be even and give an even number? And the answer is only one of these is a possibility. An odd over an odd cannot give an even. Now, how do I know that? Well, I could do some examples to prove it, but notice if I move this odd to the other side, this statement would be saying that an even times an odd is equal to an odd. That just can't be the case, right? Evens are multiples of 2. Any number times a multiple of 2 will itself be a multiple of 2, will have to be even. So I've eliminated one of the possibilities. M and n cannot both be odd, therefore they have to both be even. That's the only scenario that fits both of these possibilities. Okay, great. So which of the following cannot be an even integer? Let's see, maybe this is enough to answer the question. So now how am I going to analyze these answer choices? Well, which cannot be an even integer? So maybe what I can do is try to make it an even integer. And if I fail, it has to be the right answer. But if I can even under one circumstance make it an even integer, it's not the right answer. Okay, so let's look at A. Could this be an even integer is kind of what I'm asking myself. Now let me break it up. It might be easier to analyze answer choice A if I think of it like this. So could this be even? Well, what I know about m and n is that they're both even. So an even over 2, is that going to give an even or an odd? And I pretty quickly realized it could go either way, right? 4 over 2 gives an even number, but there's also even numbers that divided by 2 give odd numbers, right? 6 over 2 equals 3, that's an odd number. So an even over an even could give an even or an odd, and that's true for m and n. So could this yield an even number? Well, sure, right? If they're both even, then I could get an even number. If m over 2 and n over 2 are both odd, odd plus odd is even. So, not every scenario is going to give an even number, but there are some scenarios where I get an even number here, and I'm looking for which of them cannot under any circumstances be even. So A doesn't fit the bill because it could be even. Okay, what about m over 2? Well, notice I kind of already analyzed that, right? I said that m over 2 could be even or odd. So it could be odd, but it could be even. Well, if it could be even, it's not the right answer, because I'm looking for which one just cannot possibly be even. Okay, with C, let's kind of analyze this in a similar way that we did A. Let's split n plus 2 over 2 up. N over 2 plus 2 over 2. Okay, so n over 2 plus 1. Could this be even? Well, again, an even over 2 could give an odd, and an odd plus an odd would give an even. So there's a circumstance where C is even. That's gone. What about m plus 4 over 2? Well, let's do the splitting up method again. M over 2 plus 4 over 2 would be equal to m over 2 plus 2. Okay, m over 2 could be even or odd, but again, if there's a circumstance where I could get an even number here, then D is not correct, right? I could get an even plus 2. That would give an even. And with E, I've got m over 2 plus 3. If I split that up, and I'm going to run into the same problem again here, right? M over 2 could be odd. An odd plus an odd is giving an even. Okay, so I struck out here. I figured out that m and n are both even, but that wasn't enough to actually answer this question. Okay, so I've got to go back to the drawing board and see, is there anything else I can figure out about m and n that's going to be more specific? And once I figure that out, maybe that'll help me pick an answer, because what I've done so far just wasn't enough to pick an answer. Okay, so m over n has to be even. Maybe if I analyze that further, I could figure something out. And from these examples, I remind myself, well, an even over an even, in theory, could give an even or an odd. But m has a value that when I divide it by n, another even number, I'm getting an even. So it seems like m is more like 4 than like 6. So let's explore that a little further and see, okay, what are even numbers that when I divide them by 2, an even number, also give an even number? Because m is going to have to be like that. Okay, so here are a bunch of even numbers. If I divide them by 2, an even number, what do I get? Well, I get 1, 2, 3, 4, 5. Okay, and what do I notice about these? Well, only every other one is going to be an even number. Okay, so m is going to be like these even numbers, the one that when I divide them by 2, an even number, give an even number. So what do I notice about all these numbers that are kind of like candidates for m? They're all multiples of 4, right? Non-multiples of 4 divided by 2 give odd numbers. But I know that m, when it's divided by an even number, is giving an even. So long story short, m has to be a multiple of 4. Not just an even number, but an even number that's also a multiple of 4. So that's a lot more information. Okay, great. So maybe I'll just note that down. M is a multiple of 4. This one, I could probably go back into these answer choices and see, all right, maybe that opens things up. Maybe one of these is now clearly going to jump out as the right answer. Now, before we do that, let's consider another sort of method here. Now, notice what I kind of did here was, you could say, quote unquote, the stupid method, right? I was writing out possible even numbers and seeing which ones, when divided by 2, give an even number. Great, I find a pattern. But is there a more formal algebraic way to do that? Well, let's look into that. So here's again my expression. M over n gives an even number. So what is an even number? Well, an even number is a multiple of 2. So I could say, okay, let me pick 3 integers x, y, and z. And this is essentially saying m over n is an even, that 2x over 2y equals 2z, right? These are all even numbers, so this would have to be true. Now, what can I find out more specifically about m? Well, if I rearrange this, what do I get? 2x equals 2y times 2z. What is that? 4yz. Okay, now 2x was just a stand-in for m, so I'll just rewrite this. M equals 4yz. Okay, now I said x, y, and z are all just integers, so m is equal to 4 times an integer. Thus, m is a multiple of 4. Okay, so 2 different pathways to get to the same endpoint. M is not just even, it's also a multiple of 4. One of them, write out numbers, look for a pattern. The other one, do some formal algebra and arrive at the same conclusion. I think either one works great, whichever one seems more appealing, whichever makes more sense to you. Okay, so let's go through these answers again with this new bit of information in mind. M is a multiple of 4. Okay, so if I have a multiple of 4 over 2 plus an even number over 2, what do I know about that? Well, multiples of 4 over 2 divided by 2 have to give even numbers. Even numbers over 2 could give an even or an odd. So again, this one could be even, so it's, still not A. What about B? Well, a multiple of 4 over 2, we said, is even. So this, not just could be even, but this one actually has to be even, so definitely not B. Okay, what about C? Well, nothing really changes from our last analysis, right? The same logic still applies. An even over 2 could give an even or an odd, plus, this should be a 1, plus an odd number 1. Well, if it's an odd plus an odd, it could be an even. Nothing is new there. C is still out. What about D? Could this be even? Well, m over 2 plus 2, if I simplify it. So an even, m being a multiple of 4 over 2, that's even. Okay, so it's looking like it's shaping up to be E, but let's just analyze E to prove it. Okay, so m over 2, okay, maybe I'll just wall off E right here. E is m over 2 plus 6 over 2, which is 3. M is a multiple of 4. Multiples of 4 over 2 are even. So therefore, this is an even plus an odd. An even plus an odd has to be odd. Just absolutely has to be. There's no way E could be an even number. So let me say yes. E is correct here. Okay, great. So what do you take away from this question? Well, one thought is, again, the idea of staying flexible, right? Sometimes a formal algebraic approach works if it jumps out to you, but if it doesn't, you can also kind of get there by writing out numbers, looking for patterns. I'd also take away the idea of even-odd logic, right? They want to know which is an even integer, so I've got those even-odd rules in my head, experiment with those, see how much information I can squeeze out of this problem, out of the text here, and then work through these answer choices. And again, that leads us to the correct answer on this one of E. All right, well, thanks for checking out the video. I hope you found it helpful, gave you some tips for dealing with the basics of number properties questions. And if you're looking for some more challenging number properties stuff, feel free to check out the next one in the series, Number Properties Part 2. All right, thanks again for watching. See you next time.